Okay, today we are going to study reliability and renewal process. So the basic problem is this. For example, if you have a light bulb, like so you have a light bulb, and when you replace it first time, then it will last until it will break down at some point. So this time will be a random variable. So if you replace it, then replace with another light bulb, then it will light for some time, and after some time it will again die out. So this is a renewal process, and the reliability is the length of this light bulb working properly. So let's do it. So here's how we formulate this problem. First, let t be the random variable that represents the time until the failure of some unit. Okay. Let's say time to failure. Of, for example, of light bulb or TV set or something else, and we want to define the distribution function, the cumulative distribution function of this random variable t. So this is the distribution function is defined as the probability that component fails. At or before time t. So that is this random variable capital T is less than or equal to lowercase t. And we assume this lowercase t is non-negative. And of course, the density function of this time t is given by, so this is distribution function. And density is derivative. And we define some more terms. That is reliability. Or it is also known as survivor function. Let's call it capital RT. And this is defined as this. So it is a complement of this one. So probability that time to failure is greater than t, which is just 1 minus the distribution function. Okay. So this makes sense because reliability is the time during which the light bulb is still working. So at this time point t, it is still working, so that's the probability, this one. And let's go back to the definition of this derivative. So the density function here is given by this derivative. By the definition of derivative, we have this delta t going to 0 and t plus delta t minus f of t over delta t. So this is going back to the definition of the distribution function. that will be probability that this t time to failure is less than or equal to t plus delta t, and minus this is less than t. But if you compare this and this, these two probabilities, it is just a probability that the time to failure is between t greater than t and less than or equal to t plus delta t. So this is, okay, let's see. Let's suppose some density function. So this region divided by this width is the density. Oh, okay. Well, this should be, well, yeah. Next, we define the failure function. Or it is also called the hazard function. Okay, this is defined as this limit probability that the time to failure is between t and t plus delta t, given that the time to failure is greater than t. So this is a conditional probability. Okay, so comparing this definition of the failure function with this definition of the density function. Okay, especially look at this part. So this is unconditional in the density function, and this is conditional in the failure function. But otherwise, except for the conditional part, they are actually the same. So by comparing this, you should notice that this failure function is actually given by this expression. The density function over the reliability function. Okay, and the definition of the reliability was this. Look at this part. So this is the conditional part in the failure function. So if you remember the definition of the conditional probability in general, then this should be an immediate result. Furthermore, let's recall the definition of the reliability function. That was 1 minus ft, where this f is the cumulative distribution function of the time to failure. And so the density function is actually the derivative of f, the distribution function. So that is also, so if you compare this first equation, then you should notice that this should be the derivative of the negative of the reliability function is the density function of the time to failure. So now if you compare this with this equation, just get rid of the density part. So we have this r, the failure function, is equal to 1 over r times dr dt. So this is a kind of differential equation for the reliability function given the failure function. Okay, if you solve this, you should have this reliability function in terms of the failure function. So the significance of this equation is the following. So by some experiments, you can measure this failure function by counting, uh, by count, by measuring the time to failure many times, given these conditions. So, so the failure time to failure is greater than some time, and after that, it fails within delta t. So you count this event many times. You observe through many samples. Then you can find some estimate of this failure function. Then given that, you can calculate the reliability function based on this equation, at least in theory. In practice, it may be difficult, but yeah, that's the interpretation of this equation. Now, for simplicity's sake, let us assume that the time to failure is exponentially distributed with some parameter, let's say lambda. So in this case, the density function becomes this, lambda times exponential of negative lambda t. So the density looks like, so this is t, it's just an exponential function, like this. So the probability of failure is highest at t equal to 0 and lowest at when t is large. Okay, so in this case, we have the reliability function as 1 minus distribution function, and the distribution function is just this integral of the density. That's, and if you just substitute this density function, you should have exponential of negative lambda t. So if you plot the reliability, then it is again this exponential function. It's basically the same exponential function, but with a different scaling. So the reliability is 1 when t is 0. Of course, at time 0, then it's perfectly reliable. It should be, because nothing has broken yet. Okay, anyway, and also the failure function, lowercase r of t, is given by, now we have the density function given, and the reliability function is calculated. So if you take the ratio, then you get just a constant lambda. So that's just this function divided by this function. So what's left is just a constant lambda. So that means in this assumption, where that is the exponential distribution for the time to failure, in this case, the failure function is a constant function. Now let's recall what the meaning of this failure function was. So it was basically the probability that the light bulb survived up to time t. Okay, then after that, it will fail by time t plus delta t. So that's the meaning of this failure function. So this probability is constant in the present assumption. Okay, so every moment, the time the probability of failure is the same. So that's actually the consequence of our assumption that the exponential distribution is assumption that the time to failure is exponentially distributed. So this model is memoryless, so to speak. And in particular, let's calculate this probability. So the probability that the time to failure is greater than t plus s, given that the time to failure was already greater than s. Okay, so this is by the definition of the conditional probability. That's t greater than t plus s and t greater than s divided by the probability that t is greater than s. Okay, but this was since if t is greater than t plus s, this second condition is automatically satisfied, so we can just drop that condition. So the numerator is just equal to this, and the denominator remains. And this is the just, both numerator and the denominator are just a reliability function which we have already calculated. So that is exponential of negative lambda t plus s over negative lambda s, and that is exponential of lambda t. So note that there is no s involved in the final result. So this is another manifestation of the memoryless property of this process. So it doesn't matter how it survived up to time s. After that, that reliability is just dependent on the duration from time s to time t plus s. So the history doesn't matter. But this memoryless property is very nice because it's very easy to handle. But whether it is realistic or not is another matter. What this implies is that, for example, the light bulb does not deteriorate with time. So how long it is in use doesn't matter how likely it will break down. So until it breaks down, it will keep working just like it used to, up to that point. But in reality, it looks like many components will get kind of worn out. So the probability will be higher if you use it for a longer time. But that effect is not taken into account in this exponentially distributed model. Next, consider the problem of the mean time to failure. So that is just the expectation value of the time to failure, which is by definition this. Just t times density function and integrate. And that's it. But of course, let's make this more interpretable. So if you remember the previous result, this density function is the negative derivative of the reliability function. So we have this equals to t dr dt. Okay, then we can apply the apply integration by parts, which will give us tdr tr of t and plus and R of t. Okay, and by appropriate assumption, it should be the case that the limit, this improper integral part should be this. So when t goes to infinity, t times rt should converge to 0. Okay, and when t is 0, then this term will disappear, right? This is 0, and r of t should be finite. It's a probability, so it cannot be greater than 1. So yes. And how can we assume that? Okay, but anyway, if we can assume this, then the final result is very simple. It's just an integral of the reliability function. So that should give us the mean time to failure. Now, up to this point, we have not made any assumptions about the distribution of the time to failure. But at this point, let's assume that a very simple exponential distribution for the time to failure. And in that case, we've seen that the reliability is given by this exponential function. So if you substitute this, actually in this case, this equality does hold. And if you substitute this into this equation, the expectation value of the time to failure becomes 1 over lambda. Just integrate this over t. So far we have assumed that there was only one component in the system, and we have been discussing the reliability of that one component. But in reality, one system can contain many components which are arranged in some order. For example, in this case, there are 3 components, 1, 2, 3, C1, C2, C3, arranged in a series. So it's like a factory on a conveyor. So something goes in, and it's processed by component 1, then the output is processed by component 2, then its output is processed by component 3 before finishing the work. So in this case, we have to take into account the reliabilities of these 3 components in series. And in another example, 3 components may be arranged in parallel. So if something goes in, they are split into 3 paths. So they are processed independently in parallel, then they are put together at the end. So this is a parallel system. An even more complicated system is like this. So they are both parallel, but in each path there may be multiple components. Maybe 3, maybe 1, maybe 2 components, and they are put together in the end. Or there can be some shortcuts between 2 parallel paths. So if something goes in one of the paths, then it can go to the other path, or they can stay in the same path before going out of the system. So there's some interaction between different paths. And we want to calculate the reliability of the entire system when some system is given. Of course, there is not theory of everything, every system, but for each case, we consider some specific characteristics of the system and try to calculate the reliability of the entire system. Well then, first consider this type of system. That is, we have m components, let's say C1, C2 up to CM, these components that are connected in series. So we have something like this. So input comes here and output goes there. So in this case, let's say T is the time to failure for the entire system. So everything here. And let's say Ti is the time to failure of the component Ci. Okay, in this case, the reliability function of the entire system should be like this. Since these components are connected in series, if one of them fails, then the whole system fails. Okay, so this reliability should be given by this probability. That is, the time to failure of the first component is greater than T, and the time to failure to the second component is greater than T, and so on, and time to failure of the last component, mth component, is greater than T. So if all these conditions are met, then the system is working. Okay, and furthermore, we assume that each component's time to failure behaves independently. So because of this independent assumption, this probability simply reduces to the product of reliability functions of each component. So R1, T, R2, T, and so on. So where RIT is this probability, Ti is greater than lowercase t. Okay, so we can just split this joint probability distribution to the product because of independence. This is simply an assumption, simplifying assumption. Okay, so after all, we have this reliability function as the product of m components. Okay, so the failure rate function. Failure function is given as the negative derivative of this function. Wait a minute. Actually, it is not this, but log of this function. So that is this. If you remember, this comes from, where was it? Here, this and this. So from this you have negative dt ln r, right? So anyway, so from this we should have, let's see, that is sum of I t. No, it's not. It's so this log of r will be the sum of these individual reliability functions, and then we just differentiate it and we get the individual failure rate functions. So this is very simple. So the failure rate is just the sum of the failure rate of each component. in this series system. Next, we consider the parallel system like this one. Okay, so let's see. If we have m components in parallel, C1, C2, and Cm. So we have all these. And then we want to calculate the reliability function for the entire system based on those of each component. In this case, instead of calculating the reliability directly, we first calculate the failure. I mean, that is the distribution function of the failure time. So that is this probability. So this time to failure is less than or equal to some given time, which in this case, again, we assume each component is independent of other components. So this reliability, this distribution function becomes, first it becomes like this: T1 is less than T, and T2 is less than or equal to T, and so on, and Tm is less than T. So we calculate, because in this parallel system, even if some of the components are broken, if other components are still working, then the system doesn't stop. The system as a whole does not fail. So if the whole system should fail, then each and every component should fail. So that's what this means. So every component is failing in this case. So at the same time. Okay. So if we assume the components are independent, then this reduces to the product of each distribution function for the component 1 and component 2 and component m. So where Fit is the probability that Ti is less than or equal to lowercase t. Okay. So by the definition of the reliability function, that is R of t is equal to 1 minus f of t. Okay, and we have 1 minus product of these. So I from 1 to m Fit. And of course, each Fi is equal to 1 minus Ri. So that is 1 minus Ri. So this Ri is, of course, the reliability function of component I. Okay, so this is the reliability function for the parallel system. So let's compare what we have learned so far. The reliability function for the series system becomes like this. It is the product of the reliability function of each component. Okay, so this means if one of the components fails, so that will be in that case this Ri, one of these Ri's should be 0. Then if at least one of them is 0, then the entire reliability becomes 0. So the system fails. And in the case of parallel system, even if one of the reliability function becomes 0, it's okay. So in that case, it will be one component will be 1, but every other component will be less than 1. So still, this product, okay, maybe I should say this, something like this: 1 maybe two component case would look like this. So 1 minus R minus 1 R2. So let's say if this component 2 fails, in that case this factor will be 1. Okay, but as long as this factor is not 0, then this is less than 1. Okay, probably just 1. So as a result, this times this is less than 1, so this whole value should be greater than 0. So the system is not failing yet. But if both of them becomes 1, so if this becomes 0, then this factor becomes 1. Okay, so 1 times 1 is 1, which is subtracted from 1. Then the entire value, the whole value becomes 0. Then the system fails. So it requires all the components to fail for the system to fail. So that's the difference between the series and parallel systems. Next, what happens if we mix series and parallel components? Just like this. But in this case, we cannot define any general form of the reliability function. So we just consider this particular case where there are 3 parallel paths, and in the first path there are 3 components in series, in the second path there is only 1 component, and in the third path there are 2 components in series. So in this particular case, we can consider this as a group, this as another group, and this as yet another group. So basically we have 3 components in parallel. In that case, let's say this is group 1, group 2, and group 3. Okay, so we can apply the logic of the parallel system, in which case the reliability function should be something like this. So for the first group, we have the reliability of the first group, okay, and times 1 minus reliability of the second group times the reliability of the third group. Okay, now in each group, in the group 1, it is a series of 3 components. So we apply the logic of the series system. And in that case, this RG1 is just the product of each component, first component times second component times third component, right? So just the product of this and this and this. And for the group 2, it's just there's only component 4, so the reliability function of the group 2 is just the reliability of the component 4. And for the reliability of group 3 is the reliability is product of reliability of 5 and 6. So 5 and 6. So after all, the entire reliability of the whole system becomes 1 minus and 1 minus this. Let's see. 1 minus this and times 1 minus R4 and times and 1 minus this. So this would be the reliability function for this particular system. So we have to consider each system based on some particular characteristics of systems. As a final example, consider this system. So here there is this component C3, which is a bridge that connects two parallel paths. So when everything is working, every component is working fine, then system can go this way, or this way, or this way, or this way. So there can be many ways so the work can be done. So how can we calculate the reliability of this system? Obviously, the key is this component. Okay, so let's say let's define an event WT that the system is working as a whole. Working as a whole. Okay, and let's say SI is the event that the component I is working. Okay, it hasn't failed yet. So we use the partition theorem based on the state of this component C3. So if C3 is working, then what is the probability that the entire system is working? So this is the probability, conditional probability that the system is working at time t, given that system component 3 is working. Okay, so if this is working, then we can go through this way, or this way, or this way, or this way, as long as each component that is involved in each of the path is working. Okay, so that is, let's consider some concrete cases. So for example, if let's say C1 is working, then since C3 is working, we require C2 or C5 to be working. So if C2 is working, then it's fine. If C is broken, then we can go through C5. So that means if C1 is working, okay, given C3 is working and C1 is working, then either C2 or C5 should be working. So C2 or C second component is working, or the fifth component is working. So if C1 is not working, then C4 should be working. Otherwise, there's no way out. Okay, and in this case, also C2 or C5 should be working. So as a result, we require that this probability should be equal to either C1 is working or C4 is working, and C2 is working, or C5 is working. Okay. So this probability should be equal to this probability. Okay. And also the reliability of each component is independent of other components, as we usually assume. Okay, then we consider the case where C3 is not working. So that's complement of C3. In this case, we cannot go through the bridge. So this is not usable. So that means we have to go through either this or this path. So in the first path, this C1 should be working and C2 is working. Or C4 is working and C5 is working. So that is this probability. So C1 is working and C2 is working. Or C4 is working and C5 is working. Okay, again, C3 doesn't appear on the right hand side because all these components are independent from C3. So the reliability function should be therefore expressed as this. So first this probability Wt given S3 times S3, right? Given that S3 is working, the system is working, times component 3 is working. Or the second probability, if the component 3 is not working, then the system is working. And S3 bar, complement of S3. So S3 is broken. But this probability is 1 minus this probability. So let's replace that. So S3. So this should be the form of the reliability function of this particular system. Now let's calculate this in more detail. So this first term here is this. Okay, so let's put this probability of S1 or S4 and wait a minute, so this should be S actually. It's confusing, but yeah, so S2 or S5. Okay, so since all the components are independent, this conjunction can be split into the product. Okay, so S1 or S4 times S2 or S5. Okay, and so this probability is in general, so the probability of union is given as probability of S1 plus probability of S4 minus probability of the intersection. And the same for the second term. That's probability of S2 plus probability of S5 minus the intersection. 2 and S5. And again, by independent assumption, this is the product of S1 and S4. So we have probability of S1 plus probability of S4 minus probability of S1 times probability of S4 times probability of S2 plus probability of S5 minus probability of S2 times probability of S5. Okay. Next, we assume that each of these probability, each component is identically distributed as other components. So all these probabilities should have the same functional form. So that is, so this is basically the reliability function of each component, right? So let's call this as RC. Let's see. So let's us call this RC. So it's the reliability of each component. So all this should be the same function. Okay, so that means this is equal to this plus this is 2RC of t, and this is RC squared. and everything is repeated, so everything here is squared. And for, wait a minute, for this part, let's consider this probability, that is this one, S1 and S2, or S4 and S5. So let's calculate that. So probability of S1 and S2, or S4 and S5. So that should be probability of S1 and S2 plus S4 and S5 minus probability of S1 and S2 and S4 and S5. Okay. Now, again, using the independent assumption, this can be split into the product. S1 times S2 and S4 times S5. And this one, we just have conjunction here, so it's just a product of 4 components. Okay, so that's minus probability of S1, probability of S2, and probability of S4 and S5. But again, we assume each component, all the components are identically distributed, so each of these probabilities have the same functional form, that is RC of t. So that will be RCt squared from here, and another RT squared, so that's 2, and this is RC to the power of 4. Okay, so that's this conditional probability. So, and again, this one is RC, and this one is 1 minus RC. So this one is RC. So we just plug in all these terms, and the final result should be, it's a little bit complicated, so it should be, let's see, that is, okay, 2RC, RC squared, everything squared, okay, 2RC minus RCT squared, everything squared, times reliability of component 3. So it could be the same as RC, but just leave it like this way. And the other part is 2RC, this one, squared minus RC to the power of 4, and times 1 minus R3. So this should be the final result. Anyway, so apparently it's not an automatic process. It's not just a simple application of some formula. You have to build the reliability function on case-by-case basis. Next, we consider renewal processes, which is a process where we replace failed components with a new component. Okay, so every time a component fails, we replace it with a new one with the same property. Okay, so let's say starting from t equal to 0, we start using some component. When it breaks, so there will be some time, let's call it t1, and we replace it with another component. Okay, so that will last for some time and eventually it fails. So this duration of time is called T2. Then replace with another component and it might break soon, and so on. So a basic question is, in a given time, how many renewals do we need? Based on some statistical properties of these components. Now let us define some random variables to describe this problem more precisely. And as we have already mentioned, T1, T2, T3, and so on, they describe the duration of time of each component. And the total time to failure of n components will be just the sum of these random variables T1, T2, up to Tn. And also we define n of t, which is the number of renewals, so number of replaced components up to time t at time t. Our goals will be calculating the probability distributions for these random variables, this and this, Sn and n of t. So first, to do so, let's define this random vector consisting of t1, t2, up to tn. And we want to find the probability distribution function for this random vector t. So, so the distribution function, multidimensional distribution function, would be this. Tn would be the probability that t1 is less than or equal to lowercase t1, and t2, uppercase t2 is less than or equal to t2, lowercase, and so on. And tn is less than or equal to some given time. So this is the multidimensional cumulative distribution function. And we can, from this, we can calculate the marginal distribution of each ti. Okay, let's say, let's call it t f of ti. Okay, so that will be, so we integrate over all ti's, t1, t2, up to tn, except for ti. So given this one. So that probability would be this. So probability that t1 is less than infinity and t2 is less than infinity. So that means basically every possibilities. And but we leave ti as this, less than some given time. And everything else we just integrate over all possible values. Tn less than infinity. So only ti. So this is less than some finite value, and everything else less than infinity. So that means all the values. So this is multidimensional integration of all variables except for ti. Well, I should put ti here. And let's assume all these random variables are independent. In that case, we have this tn, just the product of each random variable, each distribution function. And for the density function, so this multidimensional density function, we have just a product of each individual density functions. So assume independence. But this assumption is quite reasonable, because if we replace a component, then this duration of time should be independent of this duration of time. It's they are not related, so they are just independently picked, randomly picked components from the stock, maybe. So I think this assumption is quite reasonable. And also, for simplification in this case, we assume they are also identically distributed. So in this case, all these density functions are actually the same function. So we could write just same function, f of t1, f of t2, and so on. Now let's set out to calculate the distribution function of this Sn. But first we start from S2, because that's easier. So that is just the sum of two t's, t1 and t2. So its distribution function, let's call it f2. The variable is s2, let's say. So this should be the probability that t1 plus t2 is less than or equal to lowercase s2. And that is the integral. It's actually double integral, because we have t1 and t2. Since they're independently distributed and also identically distributed, we have x and y dx dy. So let's say x corresponds to t1 and y corresponds to t2. But what is the region for integration? That should be x is positive or 0, and y is positive or 0. And also x plus y is less than or equal to s2 because of this restraint. Okay, so this can be translated into this. Let's see, 0 to s2 and 0 to s2 minus y, and f of x and f of y dx dy. Why is that? So let's consider two-dimensional plane. Let's see, x and y. So we consider only x positive and y positive. So that's basically this region. Okay, so ignore the negative parts. And furthermore, we have x plus y is less than s2. So s2 here is a given constant. So let's draw this line, x plus y. So this line is x plus y equals to s2. So x plus y should be less than or equal to s2. That means we need to integrate over this area. So under this line and above the x-axis and the right of the y-axis. So we integrate this function, f of x times f of y, over this region, this triangle, over this triangle. So that means if we fix y, let's see, let's fix a value of y, okay? Then we integrate from 0x from 0 to this value. That is, what is it? So this is a point on this line, x plus y equals to s2, so that is x should be equal to s2 minus y. So this point should be s2 minus y. So we integrate this function, actually x varying from 0 to s2 minus y, 0 to s2 minus y. And y varies from 0 to s2. So this y intercept is s2. Okay, so y varies from 0 to s2, and for each value of y, we integrate x from 0 to s2 minus y. So that's why we have this. So this is, oh, okay, so this part is the integration over x, and this outer integral is the integration over y. Okay, so since this term f of y does not contain x, so we can get this out of the first integral. Okay, so this is equal to s2, and let's see, we can write like s2 minus y f of x dx and f of y dy. Okay, but what's this function? This f of x is the density function of t, and we integrate it from 0 to certain value, and that is the cumulative distribution function. And so we have here capital F of this value s2 minus y times fy and dy. So this is s2. So this is a kind of recursive equation. So f2 is defined in terms of the density function and the distribution function of one variable. Okay, and we can continue the same argument to find the distribution function for S3, that is T1 plus T2 plus T3, and you should try to derive this formula. So the distribution function of S3 is by definition is the probability that S3 is less than or equal to lowercase s3, and after some calculation it can be shown that this is the integral from 0 to s3 of f2 and s3 minus y and f of y dy, where this f2 is this f2. Okay, now I hope you get the idea. So this can be continued over and over. So in general, we have the following recursive equation for Sn. That is this probability, Sn less than lowercase sn. It is given by this integral, fn minus 1 Sn minus y and f of y. So if you have studied Fourier transform, this might look like a convolution of functions. So if you want to find the general form of this, you calculate starting from f2. Okay, since we assume we know the density function for each of ti's, t1, t2, and so on, we can calculate the distribution function of f. So this should be known. From that, you calculate f2. from this you calculate f3. From this you calculate f4, f5, and so on. Now let's try to calculate the expected number of renewals by some given time t. And to do so, we need to know the probability mass function. That is n of t equals to some given number, lowercase n. So to calculate this, we use this equality, which should be obvious. So probability that n of t is greater than or equal to n minus probability that n of t is greater than or equal to n plus 1. Right? So if we subtract this probability from this probability, we should have the probability that the number of renewals is exactly n. I think this should be trivial. But what may not be trivial is this. This probability that number of renewals by time t is greater than or equal to n is actually equal to the probability that the number the total let's see, total number of total duration of time up to nth failure, so that's Sn, is less than or equal to t. So how is that? Okay, now let's try to understand this equation. General n may be a little bit complicated, so let's try first n equal to 1. So probability of n of t, the number of renewals greater than or equal to 1 should be equal to the total time to failure is less than t, is considered this way. So this one is just t1, right? So let's draw this graph. And so first component starts from t equal to 0, and at some point there is one renewal. Okay, so this is the first renewal, and the time t is somewhere here. If the first renewal time, so this t1 is less than t, is this situation. So there may be 2 or more renewals by that time, but anyway, what we care about is this. This large capital T1 is less than the given value of lowercase t. And in this case, if this is the case, then the number of renewals is always greater than or equal to 1. Now, there is one renewal, so let's say this is renewal. So at this point, there is at least one renewal already. There could be 2 or 3 or more renewals, but in any case, this event is actually the same as this event. So consider n equal to 2. Let's see, 2. S2, that would be T1 plus T2. So there could be 2 renewals. One renewal. So at this given point of time, there were at least 2 renewals. Okay, there could have been 3 or more renewals, but we don't care as long as there are at least 2 renewals. So the number of renewals is at least 2. Okay, so it could be somewhere, t could be somewhere here, but still we have at least 2 renewals. And this t1 and this t2, this summation is less than or equal to this given value t. So this applies to any value. So therefore, in general, we have this. Sn less than or equal to t is the same event as the number of renewal at time by time t is at least n. So if we use this relation, calculating this probability using this expression becomes easy. So this probability that n of t is exactly equal to n is given by this probability minus n of t is greater than or equal to n plus 1, which are equal to this probability. Sn is less than or equal to t minus probability that Sn plus 1 is less than or equal to t. Okay, so and we already calculated, we already have shown how to calculate this probability. So this is the cumulative distribution function, fn of t, and this is fn plus 1 of t. Okay. So finally, we can calculate the expectation value of the number of renewals. So by definition of expectation value, this is n times probability of n of t equals to n. Then we substitute this expression here. Then we have fn of t minus fn plus 1 of t. Okay, but if we expand this one, let's see, starting from n equal to 1, we have f1 minus f2. So that's the first term. And the second term, we have 2 here. And f2 minus f3. And we have 3 and f3 and minus f4 and so on. Okay, but now we have f2 here, and we have f3 here and here. So if you add these two f2 terms, then negative 1 and positive 1, positive 2, so that will positive 1, and negative 1 and positive negative 2 actually. Here we have 2. 2 times negative 1 is negative 2, and 3 times positive 1 is 3. And if you add them, just positive 1. So after all, we have this f1 plus f2 plus f3 plus and so on. So that is just the summation of all those distribution functions from n equal to 1 to infinity. So the next step is to calculate this series of cumulative distribution function. But although we have given how to calculate this based on a recursive equation, we don't know any explicit expression for this distribution function. But there is a nice trick. First of all, we have the density function for n. So we just differentiate this distribution function with respect to t. And this would be equal to this. So you should try to prove this. And f of y dy. And I think this should be trivial. Okay. And so, for example, f2, if you calculate this way, it will be, so f1 is same as f, so it will be ft minus y, fy, and dy. And let's say we approximate this function by the exponential distribution. So let's say f of t is equal to lambda e to the power of negative t. Okay, this exponential distribution. Now, this is just a simplifying assumption. Okay, if this is the case, then you plug this into this integral. Then you have f2 equals to lambda squared times t exponential of negative lambda t, which is gamma distribution with parameters 2 and lambda. Okay, and if you continue this, in general, we have fn of t as gamma distribution with parameters n and lambda. You should try to prove this by induction or something. Okay. So, if we know this, then we can go back to the calculation of the expectation value of renewals. So that was the sum of the distribution functions. But this distribution function is the integral of the density. I should use a different variable. Okay, then at this point we swap the order of summation and integral. That is first sum, then integrate. Okay, but if you have this expression and if you carry out this summation, and you should prove this, that is equal to actually just lambda. It's a constant. So after all, we have just wait a minute. It's not infinity, it's t. So after all, we have lambda t as the expectation value of the number of renewals. But doesn't this look familiar? So if this number of renewals follows the Poisson distribution with parameters lambda t, then this will be the expected value. So actually, you can show that this is indeed a Poisson process. Okay, so the renewal process based on the exponential distribution of each renewal time becomes Poisson distribution, Poisson process. So that's all for today.